Module 3, Lecture A, Built-in Data. By the end of this lecture, you will be able to load and inspect common built-in datasets for classification and regression, describe the structure of image, text, and multi-output datasets in Scikit-Learn, and select an appropriate built-in dataset for a modeling demonstration. Classic built-in datasets. Iris dataset. The Iris dataset is a simple, widely used example for learning classification in machine learning. It contains measurements of 3 iris species using sepal and petal length and width, which makes the data easy to visualize and interpret. Because it is clean and has no missing values, it is well suited for practicing how models predict a category from measurable features. The Iris dataset is a supervised classification dataset with 4 flower measurements as features and species labels as targets. Each row represents 1 flower, and each column represents a measurement used to predict its species. A quick review should cover the number of samples, the feature names, and the target classes, along with the measurement ranges. Setosa is usually easier to distinguish by petal size, while versicolor and virginica are more similar. The Iris dataset is useful for early machine learning practice because it shows how data structure shapes what a classifier can learn. Its 4 measurements help models identify species by patterns in the data, not by visual details. Although its simplicity may leave out expert-level information, it is ideal for learning how to load, inspect, prepare, and classify data. Python code. Iris dataset. Load the Iris dataset from Scikit-Learn and review its measurements and labels. The data contains flower features paired with target species, making it a supervised classification dataset. Inspecting the samples helps show how the feature values are used to predict the correct class. We import the Iris dataset from Scikit-Learn and use pandas to organize it in a table. These tools make it easy to load, inspect, and prepare the data for machine learning work. We load the Iris dataset using Scikit-Learn's load_iris function, which returns a dictionary-like object containing the flower measurements and their species labels. The measurements are the input data, and the labels are the target species. This makes the dataset suitable for supervised learning, where the goal is to predict a flower's species from its measurements. The code verifies that the Iris dataset has the expected size, 150 samples with 4 features each. If the data does not match this format, it raises an error to signal a problem. This check helps confirm the dataset is consistent before analysis or modeling begins. The code verifies that the Iris dataset has 1 species label for every flower measurement. It compares the number of labels with the number of data rows, and if they differ, it raises an error. This helps ensure the dataset is consistent and each sample has a matching classification. The Iris data is first organized into a pandas data frame using the feature names as column headers, so the dataset is easier to view and work with. A species column is then added by converting each numeric target label into its matching species name. This makes the dataset more readable and easier to interpret. This overview introduces the Iris classification dataset by checking its basic structure. It reports the size of the feature data and the target labels to confirm the samples and labels align. It also identifies the flower measurements used as features and the Iris species included as target classes. The Iris data is grouped by species, so each type can be handled separately. From each group, 1 representative flower is selected, its numeric measurements are rounded to 1 decimal place, and the result is printed as a clean, index-free summary, showing 1 example from each species. The script loads the Iris dataset with Scikit-Learn and checks that it has 150 flower samples, 4 features per sample, and a matching species label for each one. It then organizes the data in a pandas table with readable species names. Finally, it prints the dataset's main dimensions, feature names, and class labels, and shows a rounded example from each species to summarize the classification task. Diabetes Regression Dataset. The diabetes regression dataset is used to practice supervised learning for predicting continuous values. Each patient record includes health features such as age, sex, body mass index, blood pressure, and blood serum measures, with the target being disease progression after 1 year. This makes it useful for regression, where the goal is to estimate a numerical outcome rather than assign a category. In the diabetes dataset, the feature matrix contains patient characteristics, with each row representing one patient and each column representing one feature. The target array gives the numerical outcome for each patient, which is what the model aims to predict. To understand the dataset, check its number of samples and features, the feature names, and the range of target values. The diabetes regression dataset is useful for teaching how models predict numerical outcomes. Because the data is already prepared, learners can focus on loading, exploring, modeling, and evaluating predictions by the size of their errors. It should be used only for learning, not clinical decisions, since real medical systems require richer data and ethical safeguards. The dataset also helps clarify how regression differs from classification. Python code. Diabetes regression dataset. Load the diabetes dataset to inspect it as a regression problem. Match each row of features with its numerical target value. Then review a few compact facts about the data before building any model. We import Scikit-Learn and use its diabetes dataset loader to access a standard dataset for regression analysis. This prepares the data for exploration, manipulation, and later modeling in Python. We load the diabetes dataset from Scikit-Learn and return it as a pandas DataFrame for easier analysis. The dataset contains both the input features and target values needed for regression. To prepare the diabetes dataset for regression, we separate the input features from the target values. The features are the variables used to make predictions, while the targets are the disease progression scores we want the model to predict. This clear split defines the model's inputs and outputs. Before analysis, the code verifies that the feature data and target values have the same number of rows. This confirms that each feature set has one matching target. If they do not align, it raises an error to stop analysis on invalid data. To preview the dataset, select the first 3 rows from the features data, and keep only age, sex, body mass index, and blood pressure. Round the displayed values to 3 decimal places, so the preview is easier to read. This section checks the Scikit-Learn version for reproducibility, then introduces the diabetes dataset as a standard regression dataset. It summarizes the data by reporting the number of samples and features, showing a few feature names, and explaining that the target is a continuous disease progression score. It also gives the target value range and previews a small portion of the data to show its structure. This script loads the Scikit-Learn diabetes dataset for regression, separating the feature data from the continuous target score for disease progression. It summarizes the dataset by reporting the Scikit-Learn version, sample and feature counts, a few feature names, and a target value range. It also previews the first 3 rows of selected features, rounded for a quick look at the data structure. Wine and cancer. The wine dataset is used to study classification with structured numerical data. It contains chemical measurements from wines made from 3 grape varieties, and the target identifies the variety for each sample. Key details to examine include the number of samples, the number of features, and the feature names, since these connect the data to the task of distinguishing wines using lab measurements. The breast cancer dataset in Scikit-Learn is a common example for binary classification. It contains tabular measurements from digitized images of breast masses, with each sample labeled as malignant or benign. It shows how machine learning can support medical decision-making, while still requiring expert interpretation. The wine and cancer datasets are useful small examples for practicing data loading, exploring structure, and preparing models. They show how numerical features can support classification, from chemical profiles in wine to healthcare data in cancer diagnosis. They also encourage learners to think about feature meaning, class balance, and whether data is suitable for modeling, while remembering that models support expert judgment rather than replace it. Python code, wine and cancer. This script loads two built-in classification datasets and compares their shapes, features, and target labels. The output shows the key difference between a multi-class classification problem and a binary classification problem. We import two dataset loading functions from Scikit-Learn, one for the wine dataset, used for multi-class classification practice, and one for the breast cancer dataset, used for binary classification. These functions provide easy access to structured datasets for machine learning experiments. We load the wine and breast cancer datasets from Scikit-Learn's Datasets module. Each loader returns a bunch object, which stores the feature data, target labels, and related metadata. Both datasets are then ready for analysis or modeling. The code verifies that the wine dataset has the same number of rows as target labels, so every data point has a matching output value. If the counts do not match, it raises an error to stop the process. This check helps prevent problems during model training or evaluation. The code verifies that the cancer dataset has the same number of samples as target labels. This confirms that every sample has a matching target, helping protect data integrity. If the counts do not match, it raises an error to prevent problems during later analysis or model training. The code stores each dataset together with a readable name, pairing the wine data with wine and the breast cancer data with breast cancer. This makes it easier to loop through the datasets and display their information clearly. The code loops through each dataset and prints a compact summary of its structure. For each one, it reports the number of samples, features, and target classes, along with the class names. It also shows the first few feature names to give a quick sense of what the dataset contains. The key difference between the two datasets is the type of classification task. The wine dataset is multiclass, with more than two target classes, while the breast cancer dataset is binary, with only two target classes. This distinction helps define the kind of prediction problem each dataset represents. This script compares the wine and breast cancer datasets from Scikit-Learn. It checks that each dataset has matching samples and targets, then summarizes the number of samples, features, and target classes. The key takeaway is that the wine dataset supports multi-class classification, while the breast cancer dataset is used for binary classification. Special dataset formats: digits, image, data. The Scikit-Learn digits dataset shows how image data can be prepared for machine learning. It contains small grayscale images of handwritten digits from 0 to 9, with each image represented as an 8x8 grid of brightness values. This turns each image into 64 numbers, making it suitable input for classification models. The Scikit-Learn digits dataset represents each handwritten digit in two ways: as a two-dimensional image for human viewing, and as a flattened sequence of pixel values for machine learning models. Each sample is labeled with the digit it shows, making the task a 10-class supervised classification problem. The Scikit-Learn digits dataset is useful for learning image classification without spending time on data cleaning. It shows how classifiers can learn to tell similar handwritten digits apart, such as 0 and 1 or 3 and 8. Although it is too simple for full real-world systems, it introduces ideas used in tasks like postal code recognition and bank check processing. In this dataset, each feature represents a location in the image, rather than a typical measurement like age or income. Python code, digits image data. This section introduces the handwritten digits dataset from Scikit-Learn. It shows how each digit image can be viewed as a small grid of pixel values or as a flattened feature vector for analysis. It also displays a single digit to connect the visual image with its underlying numeric representation. We import Matplotlib's plotting module to create and display visualizations, and use Scikit-Learn's load digits function to access a dataset of handwritten digit images. These tools let us work with image data and prepare it for analysis. We load the digits dataset from Scikit-Learn to access images of handwritten digits and their labels. This structured data is commonly used for classification, feature extraction, analysis, and visualization. We first count how many digit images are in the dataset, then check how many features describe each image. This confirms both the dataset size and the number of values used to represent each flattened image. First, each digit image is checked to make sure it is an 8x8 pixel grid. If an image has a different shape, an error is raised to signal that the data is not in the expected format. This validation helps protect data integrity before any further processing. The code checks that each flattened digit image has exactly 64 features. If not, it raises an error to signal that the data does not match the expected format for an 8x8 pixel image, with one feature per pixel. We select one observation from the dataset, using the first item as an example. For that digit, we take its image, its flattened numerical feature vector, and its label, which gives the true digit value. This lets us compare the digit's visual form with its one-dimensional data representation. This step checks the digit dataset by printing the shapes of the image data, the flattened pixel data, and the target labels. It then shows the label for one selected example and displays its first 10 flattened pixel values as integers, giving a quick view of both the digit's label and its raw data representation. This code creates a small Matplotlib plot to display an 8x8 handwritten digit image. It shows the image in inverted grayscale with nearest neighbor interpolation, so the individual pixels remain clear. The plot is titled and labeled with pixel columns and rows. This script explores the Scikit-Learn handwritten digits dataset by confirming that each digit image is 8x8 pixels and that its flattened feature vector has 64 values. It inspects the first digit by reporting the dataset shapes, its label, and a small sample of its feature values. It then displays the digit in grayscale, helping connect the numerical data to the image structure. Linnerud multi-output. The Linnerud dataset is a classic example of multi-output regression, where one set of inputs is used to predict several related targets at the same time. It uses exercise performance measures, such as chin-ups and sit-ups, to estimate physiological measures like weight and pulse. This makes it useful for showing how real-world prediction tasks often involve connected outcomes rather than a single result. The Linnerud dataset follows the Scikit-Learn pattern of storing inputs and targets separately. But its targets include multiple numerical outputs. Each row represents one person, linking exercise measurements to matching physiological responses. While the dataset is too small for strong health conclusions, it is useful for showing how Scikit-Learn handles multi-output prediction problems. The Linnerud dataset illustrates multi-output learning, where one sample can have several target values. This idea applies beyond exercise data, such as predicting environmental conditions, product quality, student scores, or medical lab values from related inputs. The main point is that modeling related outputs together can better match the structure of real problems than building separate models for each target. Python code, Linnerud multi-output. The Linnerud dataset is used as a multi-output regression example, where each sample has multiple numeric target values. Its features and targets are aligned row by row, so each input sample matches the correct set of outputs. We import the load Linnerud function from Scikit-Learn to access the Linnerud dataset, a classic dataset for multi-output regression. It includes both input features and multiple numeric targets for each sample, making it useful for studying relationships with more than one outcome. The function provides the data in a convenient format for analysis, including use with pandas DataFrames. We load the Linnerud dataset from Scikit-Learn as pandas DataFrames, making it easier to analyze. The data is separated into input features and target outputs, so each can be handled independently. This structure is especially useful for multi-output regression, where the model predicts more than one target. Before analyzing the data, confirm that the feature rows and target rows have the same length. Each feature entry must align with its corresponding target, and if the counts differ, raise an error to signal a data alignment problem. To show that each dataset sample has multiple targets, we take the first row of the feature data and the first row of the target data, then combine them into one aligned sample. The values are rounded to one decimal place to make them easier to read. This gives a clear view of one individual's features alongside their corresponding targets. The code gives a quick overview of the Linnerud dataset as a multi-output regression dataset, where each sample has several target values. It reports the sizes of the feature and target matrices, names the input and output columns, and displays the first sample with its matching targets. This confirms the dataset structure and shows that the features and targets are properly aligned. This script uses the Linnerud dataset to illustrate multi-output regression. It loads the features and targets separately, checks that each sample has matching target values, and shows their shapes and column names. It also combines the first sample's features and targets into one aligned row, making clear that each input sample is linked to multiple numeric outputs. Faces and text. Scikit-Learn's built-in datasets show that machine learning data can include more than rows of ordinary numbers. In face image datasets, such as Olivetti faces, each sample is a grayscale image made of pixel brightness values. These two-dimensional images can be flattened into numeric feature rows, so models can process them mathematically, while the data still represents visual information. Targets may identify people or image categories, depending on the task. Text datasets in Scikit-Learn begin as documents made of words and punctuation, with each document assigned a category. To use them in machine learning, the text must be converted into numerical features, often based on word frequencies. This creates large, sparse feature sets that models can use for tasks such as classifying documents by topic. Scikit-Learn's face and text datasets show how machine learning can work with more than standard tables. Face data uses pixel-based features that preserve spatial patterns, while text data uses word-based features such as frequencies. These structures shape how we inspect the data and choose pre-processing in models, but the same machine learning tools can still be applied across both types. Choosing built-in data. Classification dataset fit. For demonstrating a classification model, choose a dataset whose target values are categories. In Scikit-Learn, the iris and digits datasets work well because they are simple, built-in, and show predictions such as flower species or handwritten numbers. Use classification data when predicting categories, and use regression data when predicting continuous values like prices or temperatures. Choose a classification dataset that matches the teaching goal. Simple datasets like iris work well for introducing basic workflow ideas, such as inspecting features and measuring accuracy. More complex datasets like handwritten digits are better for showing classification with high-dimensional image data. The goal is to support the concept being taught, without adding unnecessary distraction. When choosing a dataset for model evaluation, match it to your demonstration goals. Well-separated classes make concepts easier to introduce, while overlapping classes better reveal model limits and trade-offs. Also, consider whether a two-class or multi-class dataset is more appropriate, since each highlights different prediction tasks. A good dataset has clear labels and enough complexity to be meaningful without becoming unnecessarily difficult. Python code. Classification dataset fit. Use a simple classification dataset to demonstrate basic modeling. Before fitting a classifier, first compare the dataset's structure so the features and labels are clear. The iris dataset is well suited for beginner classification lessons because it is straightforward and easy to understand. These imports set up a basic machine learning workflow in Scikit-Learn. They load the iris dataset, split it into training and testing data, create a k-nearest neighbors classifier, and measure the model's accuracy by comparing predictions with the true test labels. We load the built-in iris dataset from Scikit-Learn, a common example for classification tasks. Its measurements are stored as the input features, while its class labels are stored as the target values. This prepares the data for later classification analysis. The code verifies that the feature data and target labels have the same number of rows, so each example has a matching label for classification. If they do not match, it raises an error because the dataset is not properly structured for training. The code verifies that the iris dataset has at least two classes by checking its target names. If fewer than two are found, it raises an error because classification requires at least two distinct classes. We split the dataset into training and testing sets using Scikit-Learn's train test split function. 25% of the data is kept for testing, and a fixed random state makes the split reproducible. Stratifying by the target keeps the class balance similar in both sets, which supports more reliable model evaluation. Create a k-nearest neighbors classifier using 5 neighbors, a common simple starting choice. Then train it with the feature data and matching labels so it can learn patterns and make predictions on new data. To evaluate the model, we use it to predict labels for the test data, then compare those predictions with the true labels. The accuracy score measures the share of correct predictions, giving a simple indication of how well the model performs on unseen data. The output summarizes a Scikit-Learn iris classification example by reporting the library version, the dataset size, the number of numeric features, and the class names being predicted. It then gives the model's test accuracy, which provides a quick measure of how well the model performs on unseen data. This script shows a simple machine learning classification example using the iris dataset. It loads and checks the data, splits it into training and testing sets while preserving class balance, and trains a k-nearest neighbors classifier using 5 neighbors. The model then predicts the test labels and reports its accuracy, along with basic dataset and Scikit-Learn version information. Regression dataset fit. Regression datasets are used when the goal is to predict a continuous value, such as an amount or rate. In Scikit-Learn, they show how models learn relationships between input features and numeric outcomes. Unlike classification, which checks whether labels are correct, regression evaluates how close predictions are to the actual values. When teaching regression, choose a dataset with familiar features, such as income, room counts, housing traits, or health measurements, so students can connect inputs to the target outcome. A moderate-sized dataset works best for beginners because it shows useful variation without becoming overwhelming. The dataset should match the lesson goal, whether students are inspecting data, fitting a model, or comparing algorithms. Choose a regression dataset that matches the goal and complexity of your demonstration. Simple datasets work well for teaching basics like splitting data, training a model, and evaluating errors, while more complex datasets can show why preprocessing, validation, and model choice matter. The key is to select data that supports the concept you want learners to understand, such as trend fitting or comparing model flexibility. Python code. Regression dataset fit. This example uses regression data, where the goal is to predict a continuous numerical value. A simple model is used, so the prediction error is easy to see and understand. We import key Scikit-Learn tools for a simple regression workflow. The diabetes dataset provides sample data. Linear regression creates the model. Mean absolute error measures prediction accuracy. And train test split separates the data so the model can be tested on examples it did not see during training. We load the diabetes dataset from Scikit-Learn as a pandas data frame, which makes it easier to work with the numeric regression data. The input features are separated from the target value, which is the outcome to be predicted. This prepares the dataset for later processing and model training. Before training, the code checks that the feature data and target values have the same number of rows. This confirms that every feature set has a matching target value. If they do not align, it raises an error to prevent unreliable model fitting and protect data integrity. We split the dataset into training and testing parts using Scikit-Learn's train test split function. 75% of the data is used to train the model, while 25% is kept for testing. A random state of 42 makes the split reproducible across runs. We create a Scikit-Learn linear regression model to predict continuous values from input features. Then, we train it on the data so it can find the best fitting line, reducing the gap between predicted and actual target values, and learning the main patterns in the training set. The trained linear regression model is used on the test data to predict continuous target values. Its performance is then evaluated with mean absolute error, which shows the average size of the differences between the predictions and the actual values. The output reports the Scikit-Learn version for reproducibility, then identifies the diabetes regression dataset and its number of rows. It explains that the target is a continuous disease progression score, so the task is regression. Finally, it gives the test mean absolute error, rounded to 1 decimal place, to summarize the model's average prediction error. This example shows a simple linear regression workflow using Scikit-Learn's diabetes dataset. The data is split into training and test sets. The model is trained on the training data, and its predictions are evaluated on unseen test data. Performance is measured with mean absolute error, which shows the average size of the prediction error in the target score units. Dataset limitations. Built-in datasets are useful for teaching because they are easy to load, well-documented, and usually clean. However, they are often simplified and do not reflect the messiness of real-world data, such as missing values or complex collection conditions. Use them to support a specific concept or modeling workflow, not to represent professional data science practice. Built-in datasets are useful for learning because they are small and quick to train on, but they can give a misleading sense of model reliability. Their limited size may hide problems like high variance or weak generalization, and their data may reflect outdated conditions or historical biases. Use them for practice, but avoid drawing broad, real-world conclusions from their results. Built-in datasets are useful for teaching machine learning basics, such as data splitting, comparing algorithms, and interpreting accuracy. However, they should be chosen to match the lesson and presented with clear limits, since they are not meant for real-world decisions. Small, balanced classification datasets can highlight training mechanics, while topics like deployment or fairness require added context about bias and errors. In this lecture, you learned to Load and inspect common built-in datasets for classification and regression. Describe the structure of image, text, and multi-output datasets in Scikit-Learn. And select an appropriate built-in dataset for a modeling demonstration. In the next lecture, Lecture B, we will go over generated data.
Thank you for your attention. See you all in the next lecture.